Hi, Jerry.
Good evening.
There was a request from some team members if you could record this session. I guess they couldn't join today, so if that's possible.
Yeah, every session is recorded.
Okay, thank you.
Yeah, they can find the link on the modules tab on Canvas.
Thanks.
Yeah, are there some exams coming up or some other plans in the program?
We just had one exam last Saturday.
Oh, I see. I hope you all did well.
Let's hope.
Hello, Jerry. Hi,
Hi,
Yuchi.
Kilda.
How are you?
I'm great.
Okay, I'm glad that you were.
How about you?
I could be better, but I am better than last week.
Glad to hear that.
Thank you. Hi, Yuchi.
So,
Hello.
oh, hi. If you would like to continue. Yeah, I was about to say, if you we would like to jump into the Q&A session, then we can do that on homework 5 or 6.
I have a question about problem 2, unless someone has a question about problem 1.
No, I have a question on 2 as well. Go ahead, Yuichi.
Okay. So Jerry, I have a question on problem 3. So it's saying that we have a hotel that has 50 rooms available and it can book 54. So I understand that, and there's a 3% chance that someone will not show up. So A is asking if those 54 rooms are booked, what is the probability that at least one customer holding a booking will have to be turned away? So I kind of see this problem as, if I have 54 rooms, what is the probability that 50 people will be, what is the success of 50 people actually booking the room? Is that a wrong way to think about that?
It may not be wrong, but it seems slightly difficult for me to follow this rationale. You said you assume there are 54 rooms. Then it's quite different than what we are given, that the hotel only has 50 rooms. So I would think it's a better idea to figure out in this problem 3, what is the variable and what are the parameters, so that we know what distribution we should look into, right? So as you can see, it might be very useful to figure out which one of the given quantities correspond to which parameters and variable. So in distributions, we know that there are different rows of some quantities. Some are parameters that's given, that does not change until we move to a different distribution. But there are also variables. So in this example, we would use the binomial distribution because, as you said, it's about success rate, right? So here, what we are given is the success rate that's related to the chance of a customer not attending their bookings. And there is also another parameter that's the there's another parameter that the hotel only accepts 54 bookings. So the 50 rooms is a reference of the actual rooms the hotel has. However, it's not a parameter for the binomial distribution. And the variable that's sort of most important is either the people who did not attend their booking, or we could define it as the people who actually attended their booking. So the event or the success rate is quite arbitrary. We could define it either way. So we could use either the 3% chance to miss a booking or 93% of the chance to not miss any booking.
So I calculated, right? So out of the 54 bookings that were already booked, the success of all 50 people showing up was 92%, that I would get more than 50 people to show up for their booking. So that means that I have a 92% chance that at least one person or more has to be turned away. Is that correct thinking?
Yes. Oh, I see. Yes. So in this part, I think it's part A. It's slightly challenging but very important to translate what the question asks for to some distribution or probability. As you said, the question asks for at least one customer holding a booking that will be turned away. And you did a good job to translate it into that more than 50 people of the 54 bookings showed up. So it's a great way to work around or to interpret the question.
I see. Okay.
Yeah, so did other students have the same thinking and rationale when working on problem 3, part 1, part A?
Well, I was working with the 93%, and why I don't
93, excuse me. Maybe you were talking about 97%?
No, I mean the 97%. Now my question is, where does the 92 come from? How do you get the 92%?
Oh, I see. Yeah, she mentioned 92% because that's the cumulative probability related to more than one customer being turned away. So more than one means there could be 1, 2, 3, or 4, because we only accept 54 bookings. So if one customer was turned away, that means there were 51 people showing up out of the 54 bookings, right? But there could be also 2 customers being turned away. So that means out of the 54 bookings, we had 52 customers showing up. So we follow the same rule, then we go up to, into 54. So here we are examining the chance of the collective or cumulative probability of either 51 or 52 or 53 or 54 customers showing up.
So in other words, it will still be 92%.
This 92% is the cumulative of all these 4 scenarios. It has it's related to the 97% of average chance of not showing up, but it's not the same concept.
Okay. I think I'll have to go back to the video.
That might be a good way to review the content.
Right.
So did other students have different thoughts or different methods to work on this problem? All right, so if not, I will challenge you to provide me some candidate answers for problem 1. I noticed that in the other class, the full-time MBA, a few students were not able to interpret the false negative rate correctly. So I wonder whether you could do this one well, because it's quite important to understand these terminology before heading to problem 2, where you need to use them.
Hi,
So,
Donna, I can
hi,
try.
Donna.
Yeah, I
Yeah,
can try.
sure.
Are you asking me to, yeah. So false, the question is, let's see.
What
False
does,
negative rate, yeah.
yeah,
What
what
does
does it
this really
mean?
mean? Yeah.
Mhm.
So false negative indicates that 5% of the time that the test result is going to be a negative for a person who actually does have COVID.
All right.
And so the information that would be, you'll need to know is the probability of having COVID.
Mhm.
And then you can multiply those things together.
Wonderful, excellent answer, Donna. So did the other students agree or disagree with what Donna said? Did you have the same answer or slightly different ways to interpret a false negative rate?
So I didn't catch all of what Donna said because maybe I wrote it differently because I know I was kind of having problems just understanding it, but I essentially said that 5% means that out of all the negative tests, 5% is incorrect. So 5% is actually positive that has a negative reading.
I see. All right, up to now we have 2 candidate answers. Do we have more different ways to interpret this terminology?
Yeah, I agree. I just use the tree. Basically, you don't. So first of all, they don't give you the probability of people with COVID and without COVID, and even the probability of people with COVID who test negative is 5%. So you can figure out the probability of COVID people who are actually test positive at 95%. But on the other hand, on the other side, you don't have the entire population of people who don't have COVID and test positive and don't have COVID and test negative.
I see. Well, okay. It seems we have a diverse answers on this question already. Then, unfortunately, not all of you are correct, because it's very important to address this false negative rate or any other alternative ways. Complementary ways, either true positive or false negative or true negative rates. All these are what we know as conditional probabilities. So it's very important to interpret them correctly in this way, by understanding them as conditional probabilities. So I would like to show you a very helpful way to understand them correctly and also apply them easily by using some equations. So here, I made a worksheet to illustrate some of these terms. So in question 1, we have the false negative rate, right? So the answers provided by Donna was correct. Because she interpreted this false negative rate as only relevant to the people who are actually infected with COVID. Behind this vertical bar is what's being conditioned. Being conditioned, it means that behind this bar, it's a known event. So people with COVID infection is already a certain event. So we only assess whatever probability among these people. So those who actually do not have COVID no longer matter. Then out of these many people or residents who actually have COVID, what's the percentage or the chance or the probability of them going into a test but get a negative test? That's what's known as the false negative rate. So what's important again is that it's a conditional probability. What's being conditioned is people that already have COVID. So with this, it's also very straightforward to understand other similar quantities, such as a false positive rate. Can one of you volunteer to interpret what's a false positive rate means? It's very similar to what we did in problem 1 for false negative rate.
Could it be that someone already false positive? Could it be that someone does not have COVID and the test comes out positive?
You're very close to the answer. However, there's a slight distinction between what you said and the conditional probability. Because in your interpretation, you use the word and. This is somewhat similar to this one, right? However, when you use the word and, usually it's not the conditional probability. This is like the intersection of two events. So the correct way of interpreting a false positive rate is that given a person who has already had COVID, who did not have actually get infected with COVID, when he or she went to a test, he or she got a positive test. So if the other relevant but different concept that a person without COVID and get a positive test, it's different than a conditional probability. As I illustrated on the 7th row, for example, the probability of getting a negative test result and being a actually COVID infected person is calculated by multiplying the chance of getting COVID, then under this condition. So being conditioned on a person already get COVID, what's the percentage or probability to receive a negative test result? So as you can see, the probability of two events linked by and is different than two events linked by this vertical bar representing a conditional probability. So it's very important to distinguish between these two. And as I described in the beginning, all these rates, like false positive or true positive or false negative or true negative rates, are all conditional probabilities. So hopefully you don't get confused between these two things.
So what you're saying is that question 1 is referring to the condition that question. When we're looking at question 1, it has to be the conditional one.
Oh, yes.
Okay.
Yeah, and it's also related to what we need to understand for question 2. Yeah. So in
Right.
question 2, what I found that some other students were not found it not easy to go through is these two things. Let's see, maybe it's easier to put them here. All right. So let's see these things. As I said earlier, all the rates are about conditional probabilities. So among these rates, there are some relations that are important. So first, let's follow what we illustrated earlier as false negative and false positive rate, right? So on the first line, I already interpreted the false positive rate as being conditioned on no COVID, but the test result was positive. So as similarly in question 2, we are given this false positive rate, right? And some other students found the complement using 1 minus this false positive rate. But this quantity needs some examination so that we are sure we understand what it is. So in question 2, we are given the false positive rate was 1%. If we use 1 minus 1%, the remaining would be 99%. But what this 99% represents? Let's take a look. So we know that this false positive rate is only relevant to the population who do not have COVID. So among people who actually do not have COVID, there are only 2 possible test results, either positive or negative, right? So together, these 2 probabilities should sum up to 1. Therefore, the remainder for people who actually did not have COVID, but they also but they get a negative result would be this much. So these 2 things should sum up to 1. Do you all agree here? Any questions up so far? Yeah, then we do the same to understand what we get after using 1 to after subtracting the false negative rate out of 1. As we examined earlier, a false negative rate is conditioned on the on people being actually infected with COVID. What would be the probability to receive a negative test result? So among the people who actually get infected with COVID, there are only 2 possible test results, either negative or positive. So these 2 possibilities should sum up to 1. So similarly, if we subtract the false negative rate out of 1, we should get this part. Being conditioned on the person with COVID, what's the chance of receiving a positive test result. So similarly, we interpret this one as true positive rate, as illustrated here, true positive rate. So if we use the quantities given in problem 2, if we know 3% is the false negative rate, then we know 97% is the true positive rate. So whatever we take the complement, we should flip both the true or false and the positive or negative sign to get the complement. So if with 1% false positive rate, we would know that the true negative rate would be 1 minus 1%, that would be 99%. Given a false negative rate of 3%, we know the true positive rate would be 97%, as 1 minus and 3%. So these are the foundation concepts we should understand correctly. And if you need help working on problem 2, I suggest you to, as Michelle recommended, using an example of the HIV test results in the video. It'll be the same concept to use these conditional rates to find some unconditional rates or the reverse conditional rates. Yeah, that's good that Michelle used the tree example as she commented. But it's very important in the tree example to make sure you interpret these concepts correctly. I saw some students mistook some of these concepts. So they used wrong rates to multiply some other conditional probabilities. That's why they did not get the answer correct. All right, any questions regarding the conditional probabilities or the conditional rates of the test results? Oh, wonderful. It seems you all understood these concepts really well. Now maybe we can continue with problem 3 or 4.
So Jerry, in problem 3B,
Mhm.
can we rephrase this question as, out of 54 people, what is the probability that 6 people or more will fail to show up for their booking? Is that a true statement?
Yes, it sounds correct.
Okay.
Yeah, I
I
saw
get
another
something-
students also got similar answers. Yeah, so but you didn't. It didn't look good to you.
Yeah, I
Is that
got
what you mean?
some like less than 1% chance,
Oh, I see. Yeah.
which seems kind of very low, and it doesn't make sense for me.
It doesn't. Why? Because it's very low.
Right. So conceptually, I'm just having a hard time understanding, like, so there's a 3% chance out of 54 people that 6 people won't show up. I just felt like less than 1% chance was very low.
I see. So first, the probabilities can go very low for certain events that won't raise a concern. But here, what might help you to intuitively understand what might what might have contributed to a low probability is that we know there's a 3% chance, right? Only 3% of one person, a random person, booking a room, but will not be showing up, right? So if we have 6 people doing the same thing, then we need to, these 6 people would be independent from each other, right? Their decisions are not related. They do not discuss between them to decide who actually would show up or not. So this is what we call as independent events. Each event does not help to interpret other events. So we would need to multiply the chances of 6 different, six independent events. So that's why multiplying some quantities that's close or related to 30% will end up being a very small chance, right?
I see. Okay.
So I solved this differently. Can I talk to you about how I did it and see if I have some logical problems?
Sure.
Um,
Well, it may not be a problem, or it
Yeah.
can actually be logical discoveries
Oh yeah.
and
Let's
contributions.
call them that. Thank you. I appreciate that. So I used the flip. I used 97.97. So that was the chance that they would show up. And then I needed at least two empty rooms of the 50. So I needed 48. And then what I looked for was X under or equal to 48. And I got a low probability too, like 0.005.
Yeah, sounds good.
That's
So
okay. All
yeah,
right.
as we discussed in the beginning, right? I
Mhm.
said the definition of a success or an event is quite arbitrary.
Yeah.
So here it can be either a person showing up or a person not showing up.
Got it.
Yeah, so it's a similar concept that in other occasions, we may see that an event was interpreted as a success, or it could be a failure. An event could be also, or a success could be also survival or death. It could be disease or health. They would sum up to one. So we could take either one of them to define a success. But what's important is that we match the probability of an event or a success with the number of such a success or event correctly. So if we use 3% here as a person not showing up, we also need to make sure the number or X we define here is also the person, the number of person, or the number of customers who did not show up. If we used 93% as the success rate for P, if you used the statistics Excel file, then we need to make sure the X, that's the random variable, it needs to represent the number of customers who showed up to their bookings. As long as we match the probability and the number or the count of the successful events, then we can both or either ways of defining success rate would lead us to the same answer.
Thank you.
So when we talk about the, letter C, where they talk about how much per day on average you pay. So my answer for that is, or my question is really, how are we supposed to think about that holistically, right? Because if it's if it's not a high percentage, then it's a percentage of $100 per day, right? Is that kind of how we're thinking about this? Or and maybe I have the wrong numbers in here, but I'm just thinking, obviously this is meant to make us think that the probability of 54 is the magic number to get close to 50. So they're not giving vouchers away every day. Right. So but like I got 2% probability that they're going to have to pay a voucher every day. Right. I mean, I'm not asking you to tell me that answer is right, but in, the way I read this is that, how much are they expecting to pay on average? Do I just amortize that? I'm not sure how to answer that question because I got a low percentage that they're going to have to pay that.
Oh, I see. Do you mind elaborating on how you got this probability?
Unfortunately, literally my screen just went black, and the only way I can undo this is I have to shut down my computer and restart.
Oh,
and that takes a minute, so I can't.
No problem. But did you still recall how?
Yeah.
Like what method you followed?
I'll take it from memory. So I use the binomial distribution out of the spreadsheet, and
Okay.
I just basically said 50 out of 54 with the 4 out of 54 with the no-show rate.
I see.
And so that's given me 2% chance of not making 50%. The complement of that is 2%, and that's where I'm getting, the fact that on average it should be a 2% chance that if they book 54, they won't get 50, or maybe I have that wrong.
I see. Okay. Let's see what would be a good way to address this problem. But now, before that, I wonder whether other students have a similar or different approaches to this question. Part C in problem 3.
I think I looked at it the similar way with Hugh, saying if there are 54 people, what is the probability that four less people, or no, wait, sorry, let me give me a moment to think.
No problem. Yeah, I see. Sometimes these are slightly challenging because we need to make some translation between a verbal interpretation and an equation or some quantities to use. So how about other students? Did you have some alternative ways or similar ways for part 3?
So I'm gathering from this, I can't see the screen, right? It's all black. So I'm gathering from this, though, that maybe I need to rethink this one.
I see. So do you have some alternative thinking now?
I do not. I do not.
Oh, I saw there are some additional comments.
I'm sorry. So I was going to say, so out of 54 people, you want the probability of 4 or less. And so you want the probability that 4 people or less fail to show, which is pretty high. So that like you have a 97% chance that out of 54 people, 4 people or less fail to show.
Yeah, it's like 2.2%, right, Yuichi?
Right.
Interesting. Okay.
Actually, so I'm on the, when I think about it, I think the probability that more than 4 people will show up is 2.2%, but I don't think that interpretation is correct.
Okay.
Maybe because you're looking at, you have 54 people, and obviously you're looking at what is the probability. Oh, wait. sorry.
Do we go the other
maybe I'm-
direction? Do we do it 50 out of 54 and and go that way?
Mm, mm,
All
Oh,
right,
yeah.
may interrupt.
Yeah.
So I was a little lost when you somehow got either 1.1 or 2.2%. Yeah, so is it possible for maybe we should just share your screen so I understand what rationale you followed?
Jerry, is it possible? Can you kick me out of the Zoom?
Oh, I
I don't have
see.
to restart my computer. It's a lot faster that way.
Let me see how I can do so. I haven't done so before. I guess I can remove you.
Please.
I did. Oh, okay. Ah, I see. That's what you meant. Okay, okay. Now I got it. Okay, I see. Yeah, unfortunately, this did not address the problem correctly. On the like, I guess you took the value on row 11, right? So it's F11 value. That's where you got 2%, 2.2%. I see. Okay. All right. Maybe it's good if I share some methods of how I did so. Oh my God. Okay. So, or should I wait until you come back?
Yeah, we can wait.
I just removed it.
General question though, how is this problem different from A? Because
I see.
you calculated a 92% chance that at least one customer will have to be turned away. So, oh, so now you're trying to see on C, how many customers are going to be,
Hey,
what's the chance of paying $100 to each customer that
Mhm.
has to be turned away is what you're saying.
Yeah.
I see.
So let's see what's the difference here. So for problem 3, part C, right? What's different is that it matters to the amount of vouchers to be provided. So let's first define some quantities here. We know that there are 54 possible bookings, right?
mhm,
And here I would define X as the number of people showing up. So you could possibly define it as the number of people not showing up. But what matters that you match X with the success rate. So if we define it as success of showing up, then the number of people showing up should be matched with a probability of a random person showing up. That would be 1 minus this not showing up rate, right? So it'll be like 97%. Then let's see what part C requests. So if there's one person turned away, then how much does the hotel pay for such an occasion? Any thoughts?
$100.
$100.
Yeah, $100 voucher. Then does this amount change if there are additional persons or customers being turned away?
mhm.
Yes.
So what would that be if, let's see, two customers were turned away?
It will be 300, 200.
right? Yeah, so that's why it's important to examine each of these occasions. So would there be other possibilities?
Three
it-
people and 4
Three
people.
people and 4 people.
Or
All right. Is it possible that we turned away 5 or more people?
Yeah.
Good. Then this is fairly a good starting point. So if you all agree here about first the possible numbers of the customers, yeah, please just ask to them. I'm busy here. To make them plural. So we could have either 1 to 4 customers turned away. It's not possible to have more than these.
Mhm.
Do you agree? Because we only accept up to 54 bookings and we have 50 rooms. So we could only have up to 4 people who booked the hotel rooms, but the rooms are not empty. So now our job for part C would be to find the probabilities of each of them. Do you agree on these? It's important to find each of them and distinguish because the amount we need to pay for the vouchers are different for each occasions. It's not the same. So now I would like to get an answer from you to find the first probability of 1 person or customer turned away. Any thoughts on this? It should be a quick answer if you happen to have your statistics Excel file open.
So the probability of 54. Oh, wait.
$92.
Oh, I see. Oh, wait. Oh, I see. You got the answer from part A, right?
Yeah.
So, but notice the difference. Part A is that at least 1 customer being turned away. But for part C here, this question only asks for exactly 1 customer being turned away.
So
32.
Oh, so it's 14%?
Yeah, that sounds right. So yeah, notice the difference between an FX, that's the what we call as what probability density, right? And a capitalized FX, that's what we know as a cumulative probability. So for this question, because we only assess the probability of X, not X, I mean, exactly 1 person turned away, that would be translated to a probability of X exactly equal to 51.
Mhm.
Because here my X represents the number of people showing up. If you defined X as the number of people not showing up, here you should have X equal to 1.
Okay.
Yeah, so notice that here by being equal, we did not assess the other possibilities of X smaller than 51 or greater than 51. We are only interested in the probability of X equal to 51. So once we find that, we would do the same for the occasion of having exactly 2 customers turn away, or 3 or 4. Then using these probabilities, we should be able to find the amount of vouchers, the expected value of vouchers for these separately for different occasions. Do you all follow here, or any questions?
Yeah, I'm still a little unsure on what do you mean the expected value? So the probability times the value $300? Is that what we're saying here?
Yeah, exactly. So an expected value will be equal to x times by probability of x. Then we need to sum up all of these. So it'll be something like if we, yeah, but well, I guess I should probably change these symbols so you do not get confused. But notice here what these represent. Because here we are calculating the expected value of the vouchers, right? So it's related to the number of people showing up, but it's not the same. So what we need to multiply is that, for example, for the first occasion, it'll be $100. That's the value of Z times the probability of this Z equal to 100. But it's also the same as X equal to 51. So the probability of 51 people showing up is the same probability of the hotel paying 100 worth of voucher. You agree here? So we basically translate the equivalence between these two events. All right, so follow this concept, then you will be able to find the expected value of the vouchers. So here is a typical case of calculating the expected value of discrete random variables. Because as you can see here, the value of vouchers could only take 4 different values, either 100, 2, or 3 or 400. So the expected value of all these occasions is that we time the value of a voucher with the probability of observing such a value. And we need to sum over all the possibilities. That's how we get the expected value. And in many cases, it's also interpreted as the average value of the vouchers. All right, any additional questions? I did not see Hugh coming back, but I guess he can watch our discussion on the recorded video. All right, thank you for joining, and I hope you have a wonderful evening.
Thank you, Jerry.
Thank you for your help.
Thank you, Jerry.
Okay.
Thanks, Jerry.